Welcome back. I will speak today about population games. These are games with a lot of players, so many that they are modeled as continuum of players, each one of them being so small that it has a negligible effect on the others. The interesting thing with these games is that, surprisingly, they are much easier to solve than games with finite number of players. So sometimes infinite is easier than finite. I will now present an example of a group selection problem in social networks. I'll first model and show how to solve the finite player problem and then the case of population game. Assume that there is a rate of L units of content that are created per time unit, and each unit by a different source. Each source has to decide to which group to send its content. Now, group J has a size nj, and by this I just mean that they have nj members. Let small x of j be the rate of content sent to group J, and introduce the vector x whose components are the different xj's. We now introduce the spamming effects, which states that the larger the rate of information that arrives, the less the probability of a user to click on it or to watch it. So formally, we introduce the fraction pxj of the members of group J that are assumed to watch the content or to react to the content. We assume that this p is a concave decreasing function of xj. Each player wishes to maximize the expected number of views or of clicks on his content. When the number of players is finite, then this game is equivalent to a congestion game of Rosenthal, as we have already seen in the beginning of the course, and can be solved by reducing it to an equivalent global optimization problem. By that I mean that it is a potential game and it has all the advantages of being one. In a population game, the number of players is very large. It is approximated by a continuum of players. Decisions of a single player have a negligible effect on the others. Here is a similar example as the one we saw, but this time modeled as a population game. So now we assume again that there are L units of content that are created per unit of time. Again, each by a different source. But this time the size of a game is not 1 unit. It is infinitesimally small. Each source has to decide to which group to send its content, just as before. L is now a real number instead of an integer one that represents the measure of the continuum of players. How much fluid do we have? The rest of the model is just as before. The problem in this version is equivalent to a special case of what is called traffic assignment problem, which is in fact an extension of the congestion game to a continuum of players. It was introduced by Wardrop in 1952. Note that it was introduced in 1952, which is 21 years before the discrete version was introduced by Rosenthal. So here's the model. Consider a directed graph, G, that is composed of M, which are the set of nodes, and L, which is the set of links, directed links. There are K classes of traffic, and the class K of traffic is characterized by an origin OK, by a destination node dk, by a demand function L of k, and a set P of k of available paths. A path is a sequence of links that connect the source node to the destination node. We introduce yk of p to be the flow that class K sends over path P. And let xl be the total flow on link L. So there are two variables, the path flow and the link flow. We introduce the cost of the Lth link as a function of the flow that goes through it, xl, as f of L and xl. The reason we introduced link flows is that we assume that the cost of the paths is just an additive. It's the sum of the costs over each link, and that the cost of the link is only a function of the total flow that goes through that link. We introduce CPY as the cost of path P. Note that this cost depends on the amount of flow sent over all paths that have common links with the path P. Each path can be used or unused by a given class. So we say that the path is used by class K if class K sends a positive amount of flow over this path. Otherwise, we say that this path is unused by K. Let Y be a configuration of flow that is a collection of amount of flow that different classes send over different paths. So this vector Y is called a Wardrop equilibrium if for every class K and any path used by class K, the cost is the same. And this cost is smaller than or equal to that of any unused path P which is available for class K. We shall write the value of this minimum cost as A of K. I now redefine Wardrop equilibrium in terms of mathematical formulation. So it gives the following. We seek a vector Y for different Ks and different paths available to different player Ks, such that for any class J and any path which is available to that class, the sum of link costs over this path is greater than or equal to the minimum Aj, with strict equality, so it equals Aj, if Y of Lp is strictly positive. We saw the objective function, which we try to minimize, and now introduce the constraints. We see here three types of constraints. The first is the linear constraints that is based on the topology of the system, which links the path flows to the link flows. The reason we need it is because the cost is given in terms of link flows, whereas the routing decisions are taken in terms of the path flows. Then there are constraints of demand, so the total amount shipped by different paths is given by the size of this class, by the amount of players in this class L of J. And finally, the third constraint is that the path flows have to be non-negative. Before showing how to solve this type of problems, I introduce the global optimization problem, where we assume that there is just one player that sends all the traffic from all sources to all destinations. And now I'll call the link cost G instead of F, and you'll see why later. The problem is then to find the vector Y that minimizes the summation over all classes J of the summation over all paths that are available for class J of the path cost that is given as the sum of link cost along this path. The The constraints are just those that we had before. They are unchanged. We now introduce the Lagrange relaxation that can be used in order to solve this problem. One introduces the Lagrangian, which is the sum of the previous objective function that we want to maximize, plus the sum over all classes j of bj times the constraint, the jth constraint. Bj are called Lagrange multipliers. The Lagrange approach consists in replacing some constraints by putting them into the objective function instead, and by weighting them by some constant which is bj here. And now introduce the KKT theorem. KKT stands for the initial of Karush, Kahn, and Tucker. So the theorem states that there exists non-negative bj's that satisfy some complementarity relation. So for each j, either bj is 0, or the constraint that is related to the demand of that class j is satisfied with equality. So the second point is the optimality. So y is optimal for the initial constraint problem if and only if it minimizes the Lagrangian for those b that we have in the first part. These conditions hold under convexity assumption over the function g. Moreover, if it is convex, then a sufficient condition for y to minimize the Lagrangian is that its partial derivatives with respect to yjp are non-negative, and for every jp for which it is strictly positive, the partial derivative should be 0. So this gave us optimality conditions in terms of the derivatives, the partial derivatives of the global costs per class with respect to the various decision variables. We now define the partial derivative of the costs of link L with respect to the flow that goes through it. We call this FL of XL. What we just saw in the KKT equation is that the partial derivative of the Lagrangian satisfy that for each class J and each path available to that class, the sum of link costs over this path, or just the path cost, is greater than or equal to bj, with strict equality if yp is strictly positive. But now what this is exactly the characterization of a Wardrop equilibrium for the cost f, which was obtained as the derivative of g. So here are the conclusions. The first states that an assignment is globally optimal if and only if it is a Wardrop equilibrium when replacing the cost by their partial derivatives. In fact, this is what we just saw now. But this also means the following. An assignment is Wardrop equilibrium if and only if it is global optimum when replacing the cost by their integral. So that's the new link costs that I call now CLX, which are given as the integral from 0 to x with respect to the initial link costs. So what does it mean globally optimum? It means that we transformed the population game to a global optimization with these costs, where we also sum over all links L. Hence the traffic assignment problem is in fact a potential game, and this is the potential. I'll give some examples, but before that I would like to give some references and some credits to those who merit it. So there is Wardrop, who wrote his paper on this equilibrium in 1952, although this was already known or used in some way or another by Pigou, who is an economist, on 1920. Now, in the book of Beckman, Maguire, and Winston, they have shown how to transform the characterization of Wardrop of an equilibrium into a globally optimization problem. Now, Rosenthal was not aware of Wardrop and came out with the congestion game formulation of this routing game with finite number of players on 1973. Road traffic engineering have been using quite a lot of time this Wardrop equilibrium notion. The criterion that is minimized as cost is usually the delay of the journey of a car. Now, as we have seen in the prisoner's dilemma, and as is well known in finite games, also in games with infinite number of players, we don't have monotonicity. We may add a link, for example, and by adding this resource, everyone's delay increases. This non-intuitive behavior is known as the brass paradox. We'll go into this paradox in a minute, but before that, a word on what it implies. There has been an approach for maintenance of roads of investing in those points that were bottlenecks. So this was the bottleneck approach. And what the brass paradox shows is that by adding resources to a bottleneck, then at equilibrium, everyone may suffer larger delays. Brass, that was not aware of Wardrop's work, in fact reinvented the principles of Wardrop and calculated correctly the equilibrium when adding or when removing a link in a paper in 1968. There has been a huge amount of work since then on this brace paradox, and in particular let me mention the work by Kourilis, Lazar and Orda, who brought it into the area of computer science. I will now present the original brass paradox with a little more generality that will help to identify what properties of the cost imply different properties of the equilibrium. So consider here a source L and destination on the other side. There are 5 links. The objective is to transfer this L to the other side. There is only one class, therefore. Now here we see that there are 3 available paths. Either go through 1 and 3, or through 2 and 4, or through 1, 5, and 4. The link number 5 is the traversal one, which Brass showed that when removing it, then delays become smaller in the system. Now in the example of Brass, there is a symmetry in the sense that the link cost of link number 3 is exactly the same as the one of link number 2, and the link cost G of link number 1 is the same as that of link number 4. And this symmetry also will play a role in simplifying the computations here. Assume that all 5 links are there and that both the route 1-3 is used as well as the route 2-4. According to Wardrop principle, all paths that are used attain the minimum cost. So the cost over route 1 and 3 equals the cost along 2 and 4, which is our equation 1. We have here 4 nodes. I'll call them north, south, east, and west according to their geographical position. So we'll now express x5 first by the flow conservation constraints of the western point. At this point we have that x5 is simply x1 minus x3. Now at the eastern point, x5 can be expressed as minus x2 plus x4, again because of the flow conservation constraint there. Now, assume that f is linear, indeed Brace took it to be linear, then this relation also holds for the f of the x's. So fx1 minus fx3 equals minus fx2 plus fx4. So now summing this with the first equation gives that f plus g evaluated at x1 equals to f plus g evaluated at x4. And thus if f plus g is strictly increasing, then x1 has to be equal to x4. And then plugging it back, for example, in equation 1, shows that also x2 has to be equal to x3. We now make use of the conservation law at the southmost point and the northmost point. So at the south point, we have that x1 plus x2 equal L. So x2 is the difference between L and x1. So let's go back to the previous slide. We computed there x5 as the difference between x1 and x3. You can write it as the difference between x1 and x2 because we saw that x2 equals x3. So now we can use the relation in the first line to express x5 only as a function of x1, which is the unknown. So x5 is twice x1 minus L. Now, if route 154 is also used, then it turns out that gx1 plus hx5 has to equal fx2, so that the total costs along each one of the paths be equal. So we now substitute instead of x5 the expression from the first equation in this slide and obtain a relation that involves only x1. So this equation allows us to solve for x1. So to conclude, the objective that I achieved here is showing to you how one can express in a very simple way the equilibrium as a solution of a simple equation involving g, h, and f if we have some very simple properties of symmetry and linearity, which indeed were taken in the original model of Brass. To give us a better feeling, I'll go through a numerical example, the precise one that was used by Brass in his paper. So L was equal 6 there. The cost function f is given by 50 plus x. So this is the cost of links 3 and 2. And the cost g that appears in links 4 and 1 is just 10 times x. In the beginning there is no link x5, there is no link 5, so this is as if hx were infinity. In that case, and because of symmetry here, we get half the flow going through the right path and half through the left path, so it's 3 everywhere, which gives us, as f plus g, it gives us a cost of 83 at each side. Now the cost that Brace took for h was 10 plus x. So if we just keep unchanged the flows in the system, then whereas the cost along the leftmost path and the rightmost paths are 83, then the path x1, x5, and x4, its cost is 70. Hence, it's not a Wardrop, because a path that is not used, through which there is no flow, has a smaller cost than the two other paths that are used. So the path 154 attracts user from the other path because it has a delay which is smaller. So assume, for example, that there is one unit that moves from path 24 to path 154. Then the delay over path 13 is now 93. Along 24 it turns out to be 82. And along 154 it is 91. So now all three are used, but it's not a Wardrop because they all had to be the same. If they all would have to be the same if it were a Wardrop equilibrium. After this change, we still have the largest cost for the left path, 1,3. So we assume also that one unit moves from 1,3 to 154, and at this point we get that x1 equals 4, and so is x4, x2 and x3 are 2, and x5 2 as well. So now if we compute the new delays, they are all equal to 92. So this is a Wardrop equilibrium because it indeed satisfies the definition that all those paths that are used, which are now all three of them, have the same cost. So we see that the cost increase from 83 at equilibrium when link H was not there to 92 at equilibrium when H is there. We thus increased the amount of resources here and got a worse behavior at equilibrium, worse performance. So I now leave it for you as an exercise to check that indeed this is what we get also by our formula, where we reduce the problem to determining x1 through the above equation. So we finally apply this to a routing problem with two groups in a social network. So remember, this is the problem we started with. We have to decide how much we send to each one of two groups. The sizes of the group or the number of members in the group can vary from one to the other. So we define the visibility of a content at a group J if it receives xj units of content as the product between its size and j and the spamming probability, so px of j, which, as if you remember, it decreases as x increases. For one group, say group K, the visibility when sending all content to it is greater than the visibility on the other group. Note that here we deal with utilities that we maximize and not with costs that we minimize, and therefore the definition of the Wardrop here is that a constellation is Wardrop if along all paths that are used the utility is maximized and is the same. If the above condition doesn't hold, then there exists a mixed equilibrium. So this is an equilibrium in which we route content to both groups. The amount the amount x that we send to group J has to solve the following. In that case, Vj of x has to be equal to Vk of L minus x. And this is how we compute, in fact, the solution, the equilibrium solution. Just states that at equilibrium, the utilities on both paths are the same.